All right, so today's going to be a crash course in linear algebra, just the basics, and we're only going to be talking about the two-dimensional case. So shouldn't be too bad. Okay, so last time we were talking about when we can get a solution to a system of two linear equations with two variables. Ultimately, this was related to the question of if a pair of solutions comprise a fundamental set of solutions. So if we have a pair of solutions, y1, y2, okay, so is this a fundamental set of solutions? And more specifically, we want to know, can we use these with our initial condition to get a specific solution? So that's ultimately what we were trying to figure out. So we want to know if another way to put this, if y1, y2 are sufficiently independent, and we'll make that notion more precise as we go on. Independent such that any solution can be found as a linear combination c1 y1 plus c2 y2 of these two solutions. Okay, so we use the initial condition y of x0 equals y0 and y prime of x0 equals y0 prime to determine the constants c1, c2. This yields this initial condition. This yields a system of linear equations. So the first one comes from this first condition. And so if we plug in for y, we get c1 y1 of x0. So this is the y that we're talking about. c1 y1 of x0 plus c2 y2 of x0. And this is equal to y0. And then the second part of the initial condition gives us, now we want the derivative of y, so we can just take the derivative of this thing. We get c1 y1 prime x0 plus c2 y2 prime of x0 equal to y prime 0. So remember, in order to pin down a second order differential equation, we needed two pieces of information to pin down a specific solution. Okay, so in this set of equations, we know the value of, we know what y1 and y2 are. Those are our solutions, our hopefully fundamental set of solutions that we've figured out. So we know what y1 of x0 is. We know what y2 of x0 is. We know what y0 is. We know what y1 prime of x0 is. We know what y2 prime of x0 is. And we know what y prime 0 is. So we know what all these values are. And the unknowns are c1 C2. Okay, so this is a system of two equations and two unknowns. Now remember, if we were looking at a general system of two equations and two unknowns, we were writing this as ax plus by equals m, and cx plus dy equals n. So we can just sort of look at what's corresponding here. This y1 of x0 might correspond to a here, and this y2 of x0 might correspond to b. This m might correspond to this y0, and so on. Excuse me. Okay, so we talked last time about a useful kind of notation for sort of condensing all of the information that's contained in the set of equations. And that was the matrix vector equation, or matrix vector notation. So we collect together all of the coefficients from the left-hand side into a block like this: A, B, C, D. And this thing we call matrix. So this is just a rectangular grid of numbers. In this case, square actually. Okay. So this is actually a 2 by 2 matrix, where the first number refers to the number of rows, and the second number refers to the number of columns. So this is a 2 by 2 matrix. And then we collect together the variables on the left-hand side, and we write them as a column. So we can think of this thing as a 2 by 1 matrix. We also simultaneously think of this thing as the vector. You'll remember this from, for example, Calc 3. So this is the vector xy. So this is a two-dimensional vector where the first coordinate is the x coordinate and the second coordinate is the y coordinate. So for matrix vector notation, we write this as a column, just a single column, and we'll come back to why that is. And finally, the left-hand side, we just write as n. So another column. So this is again a 2 by 1 matrix here. Okay, so we're going to refer to this matrix as A, just for the sake of naming it something. And this vector right here, the vector that contains our variables, we're going to refer to as x, and I'm going to write a bar above it so that we don't confuse this x with the variable x. So this is a vector. And then this over here, our right-hand side, we'll call b. And so the way that we write this this collection of symbols here is ax equals b. And so we're writing this as as if we're doing a multiplication. And this is really the way we think about it. We think about this matrix A being multiplied by this vector x. Okay, so how does multiplication work with a matrix and a vector? The way it works is that we take this vector here and we kind of turn it sideways so that it matches up with this row. So we take this column and we match it up with this row. Oops. We match it up with that row. And so corresponding entries get multiplied together, and then we add everything up. So what this gives us is the x corresponds with the a, so that we get ax, and then the y corresponds with b, so we get by, and then we add them together. And then we do the same thing for the second entry. We do the same column multiplied by the second row, so that'll give us the second entry in the product. And so the corresponding entries this time are c and x. We get c black, dx, and then dy, get dy, and then we add them together. And so this is the result of this multiplication right here. So this is the do it in red. Result of the matrix vector multiplication. Okay. So you can think about this in your head as you take this column, you flip it on its side, and you multiply it by the row to get the first row, and then you take this column and you multiply it by, flip it on its side and multiply by the second row to get the second row. So this is the first row, this is the second row, and again, this is a 2x1 matrix. Which we can just think of as a column. Okay. So we have this thing, the left-hand side, that's the result of the multiplication, being equal to the right-hand side. The right-hand side was Mn. So these are two 2x1 matrices, which we think of as, by the way, the plural of matrices. We think of these as being two vectors that are equal to each other. So we're thinking of this as two vectors equal to each other. And what it means for two vectors to be equal to each other is just two vectors are equal precisely when their entries are equal. Okay. So when we're saying that these two vectors are equal to each other, we're saying precisely ax plus by equals m, which is just our first equation here. And our cx plus dy is equal to n, which is just our second equation. So we haven't done anything. We're not saying anything new. We're just writing it in a different way. And we'll see later on, hopefully, why this will be useful. The usefulness of this notation becomes much more clear in the class on linear algebra, but we're just going to take just what we need from linear algebra in order to do the differential equation stuff. Okay, so we can summarize a system of linear equations, right, with this matrix. Sorry, things are getting a little busy. I should just write it again. This matrix A, B, C, D. Then our variables x, y, and then our right-hand side. So this matrix vector multiplication just summarizes all of the information we already have. Now, if this system of equations has a solution, then this matrix right here, A, so this is A, x equals B, I'm just writing this bar above it to signify that these things are vectors. We mean vectors by these things. We'll say that well, let's write it like this. The system of equations has a solution. This is going to be true if and only if, so the implication goes in both directions. If this system of equations has a solution, then A has an what we'll call an inverse. And we'll write it as A to the minus 1. So if the system of equations has a solution, then A has an inverse. And if A has an inverse, the system of equations, the corresponding system of equations has a solution. So we're going to take this fact of the system of equations having a solution, and we're going to summarize it in this object, which we call the inverse of a matrix. And, well, before I try to explain what an inverse of a matrix is, I'm just going to give you the inverse of this matrix. Okay, so if this is A, this is our A, right? This 2 by 2 matrix. Then there's actually a formula for its inverse. So its inverse will be 1 over the determinant of A times the entries. We call this the entries on the diagonal. They swap. We get D, A, and then the off diagonal entries get replaced by their negative, minus B. And you'll recall from last time that the determinant of A, the determinant of a 2 by 2 matrix, is this special quantity. It's the special number that's associated with a matrix, with a square matrix. And it's determined by taking the product of these two entries, AD, and subtracting from it the product of these two entries, BC. So the determinant of A is just AD minus BC. Now, actually, it just occurred to me that you probably have seen this concept before, the determinant, because in Calc 3, this was what we used to compute the cross product. So you remember in the formula for the cross product, we used the determinant. In that case, for a 3 by 3 matrix, a little more complicated, but sometimes we use 2 by 2 submatrices in order to compute the 3 by 3 determinant. Anyway, in the 2 by 2 case, it's especially easy. We just have this formula for the determinant right here. Anyway, this thing appears in the formula for the inverse of the matrix, and I didn't mention what it means here, just to multiply a matrix by a number, right? This is the reciprocal of the determinant base, reciprocal, this quantity right here. So what it means to multiply a matrix by a number is just multiply all of the entries by that. So we could have written in the top left corner, D divided by the determinant of A, or D divided by, actually, let's show how complicated this would be to actually write it out. What a pain it would be, so that we can all agree that it will be easier to write it like this. So this is what we really mean by this. So this is just a convenient way of not having to write all of this complicated stuff. So
there's a GSM function here.
What time? Oh, I see. I teach until 11:20 here.
We can like chat outside.
Okay. Yeah, I appreciate it. Okay. All right. Sorry about that. My office is being invaded. Actually, not my office. This is the building. Okay. So this is what we have for the inverse of the matrix. Give me a second to collect myself here. anyway, we can agree that it's easier to write it this way than the other way. So we'll stick with that. Okay, so why is this called an inverse? Well, it will become clear whenever we do multiplication of this by the original matrix. So if we're writing here, so let's just start off on a new spot. A inverse times A. So this is 1 over the determinant of A times D minus B minus C A B C D. And the way that we do a multiplication of a matrix by another matrix is very similar to what we were doing for sorry guys. Actually, when I pulled in today, there was a truck parked in the parking lot, perpendicular to the direction of the parking spot. So they were taking up literally the parking spot. So today is really like the worst luck day for me. Hopefully, this is the last of it. Okay, so the matrix multiplication, multiplying a matrix by a matrix is very similar to multiplying a matrix by a vector. So what we did before to get each entry in that column, we're going to do that for each column. So the first column in the result is going to be what we get when we take this column and we multiply it by each row. Okay. So we're going to have, I'm just going to preserve the 1 over determinant of A until the end, the big reveal at the end. So we take this entry and we multiply it. I'm going to give myself a lot of room. We multiply this by the corresponding entries in the row here. So this will be our first row, first column. We'll take the first column from A and the first row from A inverse. And this will give us A D minus B C. That'll be our first entry. Should look familiar. So for the first column, second row, we'll take again, the first column here and the second row here, and we'll multiply corresponding entries add. So we'll get minus A times C. So that's that, and then plus A times C, and you can see where that's going. And to give myself a little more room. So maybe we'll zoom out a little bit. Hopefully that's still visible. Okay, so for this second column, we do the exact same thing. We take the second column of A and we multiply it by each row in A inverse. So we get B times D minus B times D. And then we get minus B times C plus A times D, which I'll rewrite as AD minus BC. Okay. Now this is, of course, 0 using the popular notation. These two things go to 0. This is AD minus BC. This is AD minus BC. And then we're dividing everything by AD BC. So what we end up with is this matrix that's just 1, 0, 0, 1. And this might be familiar to you, but if it's not, we call this thing the identity matrix. And there's a good reason why we call this identity matrix. The symbol we use for this is I. We're going to say this is equal to I. So this is the 2 by 2 identity matrix. So what happens when I multiply this 1, 0, 0, 1 matrix, this I matrix? I'll write this as I. And then I multiply this by any vector. So we'll take this vector x, y. So this is our x bar. Well, when we do the matrix vector multiplication, what we get is 1 times x plus 0 times y, right? This column multiplied by this row and then added together. You'll remember this from Calc 3 is the dot product, right? We're multiplying corresponding entries and adding together. That was the dot product. And we're doing the same thing. Very, very, very close relationship between all these. Okay, the second entry is going to be 0 times x plus 1 times y. And it's just xy all over again. So when we multiply the identity by some vector, we just get that vector all over again. And if we think about the columns of a matrix, well, if we multiply the identity by a matrix, then we just get that same matrix all over. No, that's not. No, I was just thinking, you know, those sci-fi movies where they're like a screen will pop up in front of them and they'll be like moving things around with their hands, like doing all this stuff. It'd be a lot more realistic if they were moving things. They were like, no, no, it's not working. Hang on. That's the actual future. Yeah, that'd be great if the future was like everything worked like you thought it would work. Okay. Sorry, I'm a little off balance today. Okay, so the idea is that the identity matrix acts a lot like multiplication by 1. We can almost think of this as an extension of our idea of multiplication by 1. And it's kind of nice that they kind of even look similar, 1 and I, similar to each other. Okay. Anyway, so let's see. I don't want to get ahead of myself. Now, let's return to our initial matrix vector equation. I'll leave myself a little room. So what I'm going to do is I'm going to multiply on both sides. Okay, these things are equal to each other. So if multiplication works like we expect it to work, then if we multiply by the same thing on both sides, then the equality is still an equality. So I'll multiply on both sides. I'll left multiply on both sides by A inverse. I think it's important to note here that what we get here is this on the right-hand side. This was a 2 by 2 matrix, which I'll draw like this. And then it was a vector, which was a 2 by 1 matrix. And so when we did the multiplication, we took this column and we multiplied by this row. And so corresponding entries added up. Now, if I was doing things the other way and I was saying, let's just multiply by A inverse, and we ended up multiplying on the right-hand side, what we would end up with is instead I don't know what I'm doing. I'm just going to erase. We would have a vector with 2 entries, a 2 by 1 matrix, and then a 2 by 2. And then when we try to take this column and multiply it by this row, we wouldn't have matching entries. They wouldn't have the right number. So that's an important point, which if you take linear algebra too, then you'll see that the order, unlike in ordinary multiplication, 2 times 3 and 3 times 2, doesn't matter what order we multiply them in. For matrices, the order of multiplication matters. Okay, anyway, what we get on the left-hand side here is the identity matrix times x. On this side, well, it's still the same thing. We haven't figured out what this is yet. But then this is just x, just our vector of variables. On this side, sometimes things happen on this tablet and I have no idea how it happened. Anyway, so we get this. And what we get is, right, this thing turns out to be a 2 by 1 matrix, otherwise known as the vector. And then here, it's just x, y. And so what we end up with at the end is our solution. And so what this was, remember A inverse was 1 over determinant of A, D minus B minus C A. And this B, the B bar, was our right-hand side, or our right-hand sides for our system of equations. And so if we do the matrix multiplication here, get 1 over the determinant of A, dm minus bn, that's for this entry. And then for the second entry, it will be an minus cm, right? All divided by the determinant of A. And so this gives us our solution. We get x is equal to dm minus bn over ad minus bc, and y is equal to an minus cm over ad. And hopefully this matches what we came up with at the end of class yesterday when we went through all that work trying to figure out what they are. So all of the work that we did yesterday in order to figure out what the general solution for a system of two linear equations with two variables, all of that work that we did is all being summarized in this notation. The amount of work isn't changing. We're doing the exact same work. We're just doing all the steps in different orders. So we're kind of just permuting around the steps in which we solve these things. But everything is still there. All the work is still there. It's just summarized in this notation. Okay. Now, the only thing that can possibly go wrong in this entire process is if we get a division by 0 here. In other words, if the determinant of A, which is little a d minus bc, this is equal to 0, then our system of equations, which we're summarizing as matrix vector equation here. Okay, we're still good. So then this, come on, here we go. Start writing. Okay. Has no, I don't even know if you can see that on your screen, but my screen is kind of going crazy. Has no solution. And similarly, if the determinant of A is not equal to 0, then ax equals b has a solution. Has a solution. So that's why this thing is called the determinant. It completely determines whether or not the system of equations has a solution, has a unique solution. We know it's unique. We just figured out what it was. Okay, so like I said before, I'm leaving out a lot of details of linear algebra. I'll fill them in as needed as we go forward. This is just the tip of the iceberg when it comes to linear algebra. This is the very simplest bits of it, or matrix algebra. Anyway, we're in a position now to find a specific solution, or find if we have a specific solution. So remember that we're trying to solve this system of equations. Let's, just for variety, change the color. So we're trying to find a solution to this C1 y1 of x0 plus C2 y2 of x0 equals y0, and C1 y1 prime. Sorry, I'm just thinking about how much bad luck I've had. C2 y2 prime of x0 is equal to y prime 0. All right. Now, if we can solve this system of equations, we've found a solution, right? We've found a specific solution, and our existence and uniqueness theorem tells us that there's only one solution. So if we found a solution, we've found the solution, right? Okay, so let's write this thing in matrix vector notation. So we know this thing, and what we're trying to find is this thing, right? The C1 and C2 are unknown variables. So let's just first write that as C1, C2. So that's the X bar in our matrix vector equation. So what's the matrix? The matrix is, now I'm regretting writing that first. Let's try to leave them enough room. Y1 of x0, y2 of x0, y1 prime of x0, y2 prime of x0. So we're thinking of these things as the coefficients in our linear equation, our linear forms. And then on the right-hand side, we have the right-hand side, which is y0 and y prime 0. So this is our system of equations. And we have a solution to the system of equations if and only if, now let me write this down. There's a gnat in here. Write this as we have a specific solution if and only if A inverse exists. Remember, that was what we were saying. If we had a solution, we could use it to figure out what A inverse was. And if we have A inverse, we can use it to get a solution. So A inverse exists if and only if. The only thing that could possibly go wrong in forming A inverse or finding a solution was if the determinant of A was equal to 0. So we'll say a solution exists if and only if the determinant of A is not equal. So this is our A here. And in this case, what we have is that the determinant of A is equal to the determinant of this thing, which is, and now we know how to compute the determinant. It's the product of these two. So that is y1 x0 of x0 times y2 prime of x0 minus the product of these two things, which is, you remember from the 3x3 matrix, we had that alternating sign rule. That's where this minus is coming from. y1 prime of x0, y2 of x0. Interesting to note, this looks a lot like the product rule, right? We take the derivative of one times the original of the other, and then vice versa, except in this case, we have a minus instead of a plus. An interesting parallelism. Okay, and we want this thing to be not equal to 0. Now this quantity right here, this quantity right here, this is called the Wronskian. And this is named after Joseph Maria Wronski, who's a Polish mathematician, philosopher, lawyer, economist, and occultist. And he had some interesting beliefs. Anyway, he came up with this idea of the Wronskian, and first referred to this thing in 1812, the year 1812. Okay, so the Wronskian is going to tell us whether or not our initial value problem has a solution. People are starting to pile up outside. 20 minutes left. We have time for at least one example. I might end class a little early. I was a little worried that we would run out of material to talk about today before class was over. We'll do an example. Actually, this is a good intro. Let's just start the example and I'll talk about it. So here's the example. So our ODE is going to be y prime, y double prime, minus 2y prime, minus 3y is equal to 0. Y of 0 is equal to 3. This is our initial condition. So it has two parts. The other part is the derivative of y at some initial point. And so that's what we get. Okay. Oh, I do actually, I'll give you a second to write all this down, but I want to point out something that I think is pretty interesting, which is that if we look at this Wronskian, so this determinant of A, what we see is that it's in terms of y1 at x0 and y2 prime at x0 and y1 prime at x0 and y2 at x0. The y0, these things, the y0 and y prime, y0 prime, don't enter into it at all, right? Which means that we will have, if we have a solution, if we have a specific solution, we'll have a specific solution no matter what these values are, no matter what y0. Okay. So that's an interesting fact, that the system of equations, when we look at the determinant only depends on the left, it doesn't depend on the right, whether or not we have a solution. The right-hand side doesn't move at all. So this 3 and 5, we could actually pick whatever we wanted for those values. Okay, now that I've waxed philosophical for a minute and taken up a little bit of time, continue with the example. So how are we going to solve this thing? We haven't actually talked about techniques for solving these things. We're going to look for solutions based on analogy with the way that we've got solutions previously. So we were actually given solutions previously. If you remember, the general solution that we found for y prime minus y 0 was e to the x and e to the minus x and all of the linear combinations of the two. Okay, so it was e to the power of some integer multiplied by x, or some number multiplied by x. And so we're gonna look for solutions by analogy. So we're gonna look for solutions of the form y equals e to the rx, where r is some number. Now, this actually turns out to be a method of solving these things. So this is an introduction to the constant case. Anyway, let's solve this thing. So we take this prototypical y, and I'm having a lot of difficulty concentrating because there's someone literally right on the other side of the talking. Y, let's figure out what y prime is. Y prime is r e to the rx. People in this math department, they don't care. They don't care about letting other people concentrate. It's a fact that I've learned over my 5 years in this place. Okay, so we'll compute y prime and y double prime, and we get, predictably easy answers for those things. And we'll plug them in over here. So y double prime was r squared e to the rx minus 2 times y prime, that was r e to the rx, and then minus 3 times e to the rx is equal to 0. Now we notice something right off the bat, very useful about this, what we get here, the consequence of this. And that is that e to the rx can be factored out of this whole thing. We'll do that. E to the rx. And what we're left with is something very nice, a polynomial. Okay. So e to the rx itself, we're looking for, we factor this thing. So we'll look for when the first factor is equal to 0, and the second factor is equal to 0. And the first factor is an exponential, which is never 0. So we can just divide both sides by that thing, by that exponential, and get polynomial is equal to 0. It's actually quadratic, which is especially nice because we don't get the solutions of this. So we'll do another step of factorization. Now we're really digging back into deep history. This was a long time ago that we learned to factor quadratics. And we know that this is equal to r minus 3 times r plus 1. And so we get r is equal to 3 and negative 1. And we have achieved two solutions to this thing. Y1 is equal to e to the 3x, and y2 is equal to e to the minus x. And our hope is that these two things are sufficiently independent so that we can write every solution as a linear combination of these two. Are we doing on time? All right, we'll finish this example and then we'll call it a day. Okay, so we've got these two solutions, and we're going to look for things in the form. We're going to look for our specific solution, so the thing that satisfies this initial condition, as C1 times Y1 plus C2 times Y2. Now, if we use this system of equations, the initial conditions, in order to, well, let's just write it out. So what we have is C1 e to the 3x, sorry, C1 e to the 3 times 0. So we're going to plug in our initial condition, plus C2 times e to the minus 0. This is just C1 plus C2, and that's equal to 3, right? And then our second case, we have C1 times the derivative of this first thing. So that's 3C1 e to the 3 times 0 plus negative, sure, plus negative C2 times e to the negative 0. And that gives us 3C1 minus C2 is equal to 5. So we've got our initial conditions built into our specific solution, and all we would have to do is solve this. So what we have is our matrix. Writing this in matrix notation, you could, of course, use any method of solving a system of linear equations in order to get C1 and C2. But if we write this as a matrix, so that'll be 1, 1, that's our coefficients here, 1, 1, 3, minus 1. Then we have this, really nice, easy, mentally clear way of thinking about this thing, which is determinant of A. And the determinant of A in this case is 1 times minus, that's negative 1, minus 3 times 1, that's 3. So we get negative 4, which is not 0. And so we know that this is we have a specific solution. Okay, now we can move on to the next step, which is finding the specific solution. And again, like I said, we could use just any method that we wanted to solve the system of equations. Do you have a question?
Yeah, where'd you get your second equation? The 3C1 up here.
Yeah, so let's take a step back. So this, possible I made a mistake. Let's check. We're looking at C1 times Y1 prime at x0, which is 0. I'll just write 0. Plus C2 Y2 prime at 0 is equal to 5, right? That's this. Y prime of 0 is equal to 5. So when we take the derivative of y, we get C1 times the derivative of Y1 plus C2 times the derivative of Y2. And we know what the derivatives of Y1 and Y2 are. So Y1 should be equal to 3e to the 3x. Do you agree with me on that?
Yeah, I do.
And then y2 will be negative e to the negative x. Or sorry, y1 prime and y2 prime. That's so that's where that's coming from. I'm plugging 0 in, so I get e to the 0 in each of these cases, and it just becomes 1. So I get 3 times c1 plus negative 1 c2. So I'm glad you asked. Very important to make sure that we're on the same page. Also, I'm much more in my element before asking me questions. I'm not a big fan of just like. Okay. Anyway, we have the determinants not equal to 0. That tells us that we definitely have a solution, and so we'll just find the solution. And like I said, I could do this with any method that I wanted, but I'm going to do it using the inverse. And so the inverse is going to be 1 over the determinant of A. So that's negative 1/4 times. I'll just swap diagonal and make the off diagonal entries. They're negatives, or they're multiplied by negative 1. And then I multiply this thing by my right-hand side, which was 3, 5. So instead of doing a method to solve these things, now it's just a forward sort of following steps, which, it's a matter of preference. Okay, so this is negative 1/4. My first entry will be negative 3 plus negative 5, so I'll get a negative 8. My second entry will be negative 9 plus 5. So negative 9 plus 5 is negative 4. And so when I do the multiplication by 1/4, negative 1/4, I'll get 2 and 1. So what I get from this is C1 is equal to 2, and C2 is equal to 1. Okay. Now, I guess we can stop today a little bit early. Well, actually, I'll stop lecturing. And if you have any questions or anything to talk about, we can do that. We have 7 minutes left, so feel totally free to take up. These people out here, they don't worry about them. They'll get over it.
So then once you get your constants, you just put that back into the general solution.
Yeah, exactly. So
Okay.
what we have, that's a good point. I didn't finish this problem, did I? So what we have is y is equal to 2 times e to the 3x plus e to the minus x. And this is our specific solution. This is when you look in a math paper or a math textbook and says, this is left as an exercise to the reader. We like to not finish the problem. Once we get to the point where we know how to finish it, we're like, okay, you get the point.
And then at the beginning, whenever you were doing like y is equal to e to the rx, are you using that for like all linear second ODEs?
No. So in general, okay. So there's a distinction here. In general, what we have. Well, let's scoot over a little bit. Space right here. So this is y prime minus p of x, or so y double prime minus p of x y minus q of x. I should say y prime then y, and this is equal to. Here we have it's equal to 0. So this is our general. So we have a very specific case here. Not only do we have that it's homogeneous, right? But we also have constant coefficients. And this is a very special case. So in this special case, what we'll see, and I think we'll talk about this tomorrow, is that when we're in this special scenario, we will have this always as a solution. So this y equals e to the rx will always end up with a quadratic at the end. The quadratic will hopefully have two roots, two independent real roots. And then those two independent real roots will give us the y to the ERx. That'll give us our two fundamental solutions or fundamental set of solutions. Now, a couple of things can come up even in this case. The first one is that we don't get real roots. So we could possibly get complex roots, right? And so whenever we have when we look at the quadratic formula, for example, we have a square root of something, and that discriminant could possibly be negative. So if we had a quadratic where we ended up with a square root of a negative number, we would get complex roots. Loud. So in that case, we'll talk about that. Hopefully, we'll talk about that, and we'll see that that ends up being solutions that we can consider as well. Now, in the case where we have two solutions, two roots that are the same, so we have a double root, then in that case, we'll only have one solution, and we'll have to be able to construct another solution. So I think we'll talk about that as well. Now, that's just in the case of constant coefficients, homogeneous equations. So we move on from there to non-constant coefficients, and then the non-homogeneous equation. And so the solutions end up being very similar to this, but we have to build on it using, for example, variation parameters, things like this. So that technique we've seen before. So this only works in the constant coefficient homogeneous case. And yeah, that's the answer to your question. Okay, well, I think she just disappeared. So on that note, maybe we'll end for today.
Okay, thank you.
Yep. See you next time.